Hey, what's up, guys? This is Chung here. So this time, let's quickly look at today's daily challenge problem, number 1461. Check if a string contains all binary code of size k. Okay, so the description is pretty straightforward. Basically, given like a binary string s and an integer k, return true if every binary code of length k is a substring of s. Otherwise, return false, right? So for example, if the k is equal to 2 here, right? With size k, size 2 binary string, we have 0, 0, 0, 1, 1, 0, and 1, 1, right? And with a given s here, we have all 4 substrings within s. That's why we return true here. And similarly for this second example, and for this one, 0 and 1, but for this one, it's false, right? So the range of k is 20, and the length is basically 10 to the power of 5. Right. So for this problem, I think the naive way or the regular way is just that we just since it's a size k, right? We just need to look through the entire string, and then we check all the basically all the substrings, right? And then we insert it into a set. And in the end, we simply check if the length of the set equals to what? Equals to this one, right? To this number. That's going to be the total codes, we need, and we just compare that. So that's pretty straightforward, right? So basically, we're gonna have like a code, right, to store the code we have found so far, right? So I'm gonna use a set here, and then we're gonna have a length, and now we have total, right? So total will be what? Will be we do a one shift to left by left shift by k, right? That's going to be the total number of calls we're looking for, right? And then for I in range of n minus k plus 1, right? So that's going to be we have current. So the current is going to be the s dot, we do a substring from I to I plus k, right? Then we do a code dot add, right, to this current. And then in the end, we just simply return if the length of codes equals to the one, sorry, we already have the total. Yeah. Okay, so that's going to be the naive implementation, right? If I run the code here, oh yeah, so then it's the length of s here. Submit. Right, so that's how it works, right? So I mean, for this one, as you guys can see, so the time complexity is n times k, right? Because for each of the I here, we do a substring of k, right? And that's why the total time complexity is n times k, and the space complexity is a code, right? So basically, we could have like how many? Yeah. So the time. So this is a space time complexity, right? So O of n times k, and space is also O of n times k, right? Because we have mm, yeah, because for each of the I here, we could have like a string, like different codes in this one, right? That's why the space is also O of n times k. But every time when you see this one, the substring of this one, it's gonna be a little bit slower because since we're doing this kind of substring on each of the n here, right? And I mean, a common approach to improve this one is by using a rolling hash, right? Basically, as you guys can see, right? So let's say we have if we have 1 1 0 1 0 1 1 0 0, right, and the k is equal to 3 here, if we have the first 3 letters, when we move to the next one, actually we are only removing the leftmost numbers, and then we're adding the current either 1 or 0 to the current value, right? So which means that and also since with kind of binary numbers here, if we have a k equals to 3 here, we already know the values we're looking for, right? We have 0 0 0, we have 0 0 1, we have 0 0 2, right? Sorry, not 0 0 2. We have 0 1 0, and then we have 1 0 1, and then 1 0 0. Basically this is 1 0 2 3 until 15, right? Basically we already know this is the total values we're looking for. So which means that we can use like some kind of rolling hash technique here, so that we can use O1 time to calculate basically the numbers, the value for the entire string here, which means that we're going to convert this binary string into its corresponding integer values, and we're going to save that value into the codes here. And then similarly, we only need to check the length later on. Basically, instead of storing the string itself, we store the value of that string, right? So that's going to be the improvements we can do here, which means that every time we have like previously calculated values here, right? Let's say we have what we have. This is 6, right? How can we get the values? How can we get the value from 110 to 101, right? So first, so the approach would be, so first we do a current hash. We do a left shift by 1, right? And then this 110 will become 1100, right? So for 1100, what we need to do is that we need to remove the leftmost significant values here, right? Which means that we have to, how can we remove that? We have to somehow do an AND with 1 0 0 with a 0 1 1 1, right? If we do an AND, if we do an AND with this 0 1 1 1, then we'll get 1 0 0, 0 1 0 0, and then from here we simply need to add the current values of the current digits, right, of the I index, right? We do a +1, then that's how we get 0 1 0 1, right? And yeah, so what is this 0 1 1 0? What is this 0 1 1 1, right? Actually, that happens to be what happens to be the total number of the code we're looking for minus 1, right? Because the oh, sorry, I think this one is not, 15. It's 8. Sorry, it's not 8. It's 7. Sorry, it's 7. Because if the total number of the code we're looking for is 8, right, and then 8 minus 1 equal to 7, right? 7 is exactly the same. Is exactly the 0 1 1 1. So basically, the mask we're using here is a total minus 1, right? So we do an AND with that mask, and then we just do a plus with the current value, either with 0 or 1. Okay, and then because by doing that, we can use O1 time to calculate the current hash values, right? Or the binary values, you can call it, right? From the previously state. Yeah, cool. So, and I'm going to modify this code a little bit, right? So basically, which means that we're gonna keep this one, and so here I'm going to store everything. I'm going to look through everything here, and then I'm going to have a current hash, right? So we're gonna current hash at the beginning is 0, and So here, instead of using the substring here, we're going to have a current hash is going to be equal to, first we do a left shift, right, with a current hash, with a previously hash value, and we do an AND with the mask, right? The mask will be the total, right, -1, right? And then we do OR with the current digits, which is the integer of SI, right? And then we do a code dot add current hash, right? Oh, but I think before doing that, we need to do something. We have to check if the I is either equal or greater than k minus 1, right? Because if we haven't reached the required size k substring, we shouldn't have added this code, because we might add some values that shouldn't be included, right? Yeah, I think that's all the changes we need to make here. So we can keep everything the same. If I run the code again, so this should also work. Yeah, yeah. I think it's weird. This one is even a little bit slower than the first one. Because for this one, the time complexity, the add is 01, and here's also 01, right? So basically, the time complexity for this one is going to be O of n, and yeah, but the space complexity, the space complexity, uh, let's say the space complexity. I think the space complexity, I think it's gonna be the worst case scenario is gonna be O of 2 to the power of k, right? That's gonna be the total elements we will save into this code set for the worst case scenario. Yeah. Right, cool. I think that's everything for this problem, I guess. Yep, I think I'll just stop here. Thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.